Okay, so let's begin this problem. This is example 5. So we determine the slope at C, which is here, over the support, and the displacement to free end D. So up to this point, we only have two methods to solve these kinds of problems: direct integration and conjugate beam. And let's see how direct integration might work. Well, first of all, you won't be able to write a single expression for displacement across the structure or moment. You can see you'd have to write one from A to B, and there's a hinge, and then another one from B to C, and another one from C to D. So this would be three different expressions for moment, and that would be quite a challenge for direct integration. You would generate 6 integration constants. So not impossible, but very difficult. So our second method is conjugate beam, and that seems to be the only choice we have right now. So the first step will be to draw the moment diagram for this. And you might recall that one of the first things we need to do for drawing a moment diagram is to find our reactions. So let's do that first. So I'm going to have to break this structure up, you can see, into two different components. I have a fixed connection at A, and this is a hinge at B, and a support, we'll see that's a roller at C. So I'm going to have to write a free body diagram for AB and then one for BC. Let's start over here. So free body diagram from A to B. So I'll draw that. It's of length L. And then I'll assume that I have a positive shear A and a positive bending moment at A. And at the hinge, there's no moment, so we'll assume we have a positive shear at B. And there's no load on that section. So looking here, it's only 1, 2, 3 unknowns. I should be able to solve for that. And my second free body, and this will be from B to D, will look something like this. So I've already assumed positive shear at B. It's got to be equal and opposite here at B. Then I'll have a reaction at C. Call that CY. And then a free end, and then of course there's the only thing that is applying load to the structure, this load P. Now I forgot my links there, L and L. Again, only two unknowns there, so there's a lot of different ways to proceed with this problem. You can see if I try to sum moments, say at A, I would have two unknowns, so I can't solve for that yet. Some forces in the y direction is two unknowns, so I'm kind of stuck there. So I'm going to have to start here first with the BD problem. And really what I want to find is this reaction here at B. If I can find that, that shear at B will transfer up there and make my calculations here at AB easier. So we'll start here. So I'll put a 1 here to signify this is the first equation I'm going to write. And to find this reaction at B, I'm going to sum moments at C. So again, I'll assume right-hand rule for my sign convention. And we'll sum moments at C and make sure that's equal to 0. So there's our equilibrium statement for this problem. So let's see what we actually have. Well, about C, my shear force will create negative moment, so it'll be the shear at B times the length of L. Then I've got P also creating negative moment, and that will also be PL. So it seems that when I solve for the shear at B, I get minus P. So I have a negative shear at B equal to minus P. While I'm here, I'll go ahead and do a second equation. I'll sum forces in the y direction and make sure they're equal to 0. There's my equilibrium statement for that. And I'm assuming up is positive. So I've got shear acting down, the load acting down, that's P. My shear at B is up, and CY is up. So I can put my value for the shear at B right in there. So the negative P makes this a negative. I've got 2 minus 2P. So it looks like CY is 2p. So I get these little in reverse order, but I'm keeping track of them with the numbers. So I'm going to go back to my first free body diagram and write my third equation. And now I know the shear at B. So I could find the shear at A or the moment. So it doesn't matter which one I do, but I will sum moments about A. Make sure that's 0. So there's my equilibrium. That's a little messy there, but that's basically my symbol that says right-hand rule is positive. So I'm looking at A, the moment about A, that's a negative moment with right-hand rule. And this shear at B is also creating a negative moment with the moment arm with L. So it looks like my moment at A is going to be negative shear times L, and then the shear at B is negative, so that becomes positive. So this is going to be a positive moment of PL. And then finally, my fourth equation in the sequence, I'm going to sum forces in the vertical direction, Y. Make sure that's equal to 0. So here's my equilibrium statement. Up is positive. So looking at my free body diagram, I've got shear up at A and shear down at B. That's it. So it looks like the shear at A is equal to B, and B is minus P. So there's all my equilibrium, or my reactions. So now after this is done, I can come over here and draw my shear moment diagram. So I'm going to draw a quick little template. There's my beginning and end values. And I know there's the hinge, I'm going to mark that. And there's my reaction, I'll mark that. So we'll begin with shear. Make a quick x-axis for that. And we'll start with what we know. So at A, I know the shear is minus P. So I'm going to start off here at minus P. At B, the shear was also minus P, so I don't think it's going to change. And then what's the shear at D? Well, D's a free end, it should be 0. So let's see if we can get this. So if I'm starting with minus P, I know the change in shear is the area under the load curve, which is 0. So there's no change in shear, so it should stay minus P. And of course, the slope of the shear diagram is the load. There is no load. Load is 0, so I have 0 slope. And you can see my shear at B matches my minus P, which I got here. Now the shear from B to C, the change should be there in the curve. Again, there is no change, so I'm going to stay minus P. And since there's no load, load is 0, the slope is 0, so I've got a horizontal line there. As I go from left to right, the change in shear should be this applied load, which is positive 2P. So I'll go from negative P to positive P. There's my change of 2P. And of course the change in load, the change in shear is going to be the area of the load curve, which is 0, and that gets me to P. And then the slope of the curve is given by the load. The load is 0, so here's 0 slope. So there's my shear diagram for this problem. Okay. So now let's do the moment. So I'll establish a x-axis for the moment, positive moment. What do I know about the moment? Well, I know the moment at A. I found it was PA. So it's going to start here. Sorry, PA, I meant PL. My moment better be 0 at the hinge. And then it better be 0 again out here at the free end. So I got these 3 points I need to connect. Remember from our shear force and bending moment work, the change in moment's the area of the shear diagram. In the area of this first section of the shear diagram, I'll double cross hatch it so you can see that. is base times height, which is minus PL. So PL minus PL does bring us to 0. That's good. And then the slope of the moment diagram is the value of the shear. And the shear is negative and constant, so I have a negative, constant negative slope. Now the change in moment from L to 2L would be this part of the curve, which is another negative PL. So 0 minus PL brings us to negative PL. And then the shape of that curve is given by the value of the shear. And the shear is constant, so it's straight line, and it's negative. You get that. Now the change in moment from 2L to 3L is this area in the curve, which is positive, and that's base L times height P, so that's a positive PL. So negative PL plus PL gets us to 0. That's great. We connected the dots. And then the shape of that curve is given by the value of the shear, and the value of the shear is constant, so straight line, and it's positive, so that makes this connected very nice and neat. So there's my moment diagram. Okay, so there's our moment diagram. So we've done quite a bit of work here just to get started. Now we're going to do our conjugate beam and apply this as moment to the conjugate beam. So let's make a note here. So let's draw our conjugate beam. Okay, starting at A, so our fixed connection becomes free, so we'll have a free end. Our internal hinge will become a roller. Our internal support will become a hinge, and the free end will become fixed. So we'll end up with a structure that looks kind of like this. That's fixed connection, and then I missed my roller support here. There's the conjugate beam. So the original beam, conjugate beam. So fixed end becomes free. Internal hinge becomes support. Internal support becomes a hinge. Free becomes fixed. And then I'm going to apply to my moment, my conjugate beam, as load to the conjugate beam, I'm going to supply the M over EI diagram. So what I like to do is just take that and just kind of transport it down. So I'm going to draw, or try to draw, pretty much the same shape as you saw before. So there's my moment. Now this part of the moment is positive, so that would be a positive load, so that would be acting up. And this part is negative, so that's acting down. And the value, so there's my moment. So this will be PL divided by EI. And this will also be PL divided by EI. Okay, so we've taken our original problem. We found all the reactions from statics. We have drawn the shear force and bending moment diagram. And now we've applied it to the conjugate beam. Okay, so that's probably a half to a little over, maybe close to 2/3 of the problem. So now we're going to go back and look at what the problem wants. So it wants the slope at C, which is this point right here. So I need to find the shear, internal shear at that point, and then displacement at D, and this is D. And it wants the displacement, so I need the internal moment. So really what I need to do is isolate this piece here and find the shear and moment there. So again, I can't do this. I can't draw a free body diagram of the whole structure. I'm going to have to separate it into parts also. So let's start with, let me draw a line here to kind of give you a visual breakup of that's work associated with the top, and this will be work associated with this side. So I'm going to draw a free body diagram now of section A, B, C. And if I did that, we'd see something like this. So I would have my reaction at B. That's the reaction at the roller, which is the conjugate map of the original pin. And then I'm going to have C, which is this point here, and I'm going to assume that's a positive shear at point C. And then I've got to deal with these two loads. One is up, one is down. So I'm going to indicate those. I'll call it F1. And I'll just call this F for right now. So what is F1? Well, F1 is going to be the area of this curve, which would be 1/2 the base, which is L, times the height, which is PL, over EI. And a quick calculation there gives you PL squared over 2EI. If you look at this one, well, it's the same value. So I'm going to go back and call that F1 too. So really what I need to know is just this shear here at C. Remember, I want the slope at C, and slope at C is going to be the shear at C. So let's find that shear at C. And you can do that by just doing what? Well, you can sum moments at B. So again, we'll assume right-hand rule for our moment sign convention. And we will sum moments at C. So there's my equilibrium statement. So let's see what we do. Well, the distance from B to both these forces, since these are triangular shapes, are going to be 2/3 of the distance. The distance is L. So looking at this first one, about B, they're both going to create negative moment. So I'm going to have minus F1 times 2L over 3. So that's the distance from B to here, 2/3 of L. And then I'm going to have the same thing again, looks like. Minus F1 times 2L over 3. So that accounts for the two concentrated equivalent forces. And then the reaction at C, which is also negative moment, with a length of L. So I'm trying to find that shear at C. So I can divide everything by L, that'll get rid of that. I can put the C on the other side, so we should end up with a negative value. So with L gone, I've got 2/3 plus 2/3, that's 4/3. F1 was this, so I got 4/3 of that, so I get 2, cancels with that 2, so it looks like I got 2 PL squared over 3EI. I wonder if I got that right. Let me think about this again. I don't have a calculator, so I've got, again, 4/3 L times this. That would give me 4 that, so the 4 in the numerator and the 2 in the denominator, so I get 2. So now that looks like I'm doing the right thing. So it's negative. So what it's saying now is the slope at C should be negative. Now, does that match our intuition? Well, let's think about this. Let's go back up to the original beam and let's think about how this would deflect. So I've got P pushing down. I know this has to go down. So it looks like the structure would have to bend up over and not bend here. So I'm just going to draw straight lines just to give you an idea. It's going to have some kind of curve. And then this is going to have to come out straight and bend up to meet it. And that seems to match our diagram. I've got positive curvature here. That's a positive moment. And although I didn't draw it as a curve, it should be curved and negative. So it makes sense. You can see the slope at C. It makes sense that it would be negative. So that part, at least we got that part correct. Now that can be passed on to this free body, and this will be the free body diagram of CD. So let's draw that. So what I have there, I assume positive shear at C, so I have to assume positive shear at C here. And over here I'll assume positive shear at D. I'm not looking for the slope at D, looking for the displacement, which is the moment. So there's my positive moment at D. This is length L. And again, we have that same concentrated equivalent force. Be 1/2 base times height. It's the same of all of them. So again, this is going to be F1. So to find the moment, which should match back to the displacement of the real beam, I just need to sum moments at D. So assuming right-hand rule, we'll sum moments at D. So there's our equilibrium statement. So let's execute it. So right-hand rule on my moment at D is positive. F1 is also creating positive moment. And it has a moment arm of 2/3 the distance, so that'll be 2L/3. And then I have the shear at C, which is creating negative moment at a length of L. I've already solved for the shear at C, so I can plug that in. Now it's negative, so when I plug that in, this is going to actually turn it around and create positive moment. So let's see what I get for the moment at D. So everything here becomes positive. So when I put m to the other side, this will all be negative. Now this may take me a little bit of time to do. Let's see, this term here will be 2/3 PL³/EI. And then this is going to be F1, no, similar to this up here. So that's going to be, the 2 cancels and I get 1/3. So I got 1/3 plus 2/3, oh, it's just a whole number. So it's just 1. So this should be minus PL³/EI. Okay, so I got a minus sign for the moment, which means I have negative displacement. If you look up here at the top, it makes sense that D is going down negative. Remember, our sign convention is up is positive, down is negative. So there we go. That problem wasn't too terribly long. It took me about 23 minutes to do. So maybe a little too long for an example, an exam problem, but pretty good for a homework problem. So let me know if you have any questions, email me or phone me. So until next time, take care.